Right, let's get some more physics done. It's a combined science paper. It's paper 6, which is a physics paper 2. It's the higher tier, and it's from June 2018. Question 1 here. A student uses the apparatus in figure 1 to determine the specific heat capacity of water. So there's a joule meter there, which measures energy, immersion heater, which gives out heat, and a thermometer. Part 1. State the measurements needed to calculate the specific heat capacity of water. Well, if you can, I always base my explanation on a calculation. So this calculation is the change in the heat energy equals mass times by specific heat capacity times by the change in the temperature. We need to rearrange that to find the specific heat capacity. So in order to find the specific heat capacity, we obviously need to measure the amount of energy supplied by the heater. We need to measure the mass of the water that we've got. And in order to get the change in the temperature, we need to measure the starting temperature and the final temperature. And obviously work out the change in temperature by taking the starting temperature away from the final temperature. Part 2. State 2 ways that the apparatus could be adapted to improve the procedure. Well, if you put a lid on the cup, you'll stop heat energy from being lost to the surroundings, so the heat will stay in the water. You could ensure that the heater is fully submerged, so you can see here the heater is not quite fully in the water. You could put insulation around the cup, again to make sure that whatever energy is being supplied goes into the water and not lost to the surroundings. And you could add a stirrer to mix the water up to make sure that the water next to the thermometer is not a pocket of heat or a pocket of cold. Or you could use a data logger to measure the temperature instead of a thermometer. So a data logger is like a thermometer that you hook up to a computer. Part B. The student decides to measure the temperature of the water every minute while it's being heated. And there's a graph. Minutes along the bottom, temperature up the side. Predict the temperature of the water if the heating continues up to 8 minutes. So you can see originally they've only recorded the temperature up to 5 minutes. But you can see 1, 2, 3, 4, 5, 6 results are enough to spot a pattern. So if we continue with that pattern or that trend, then it's going to roughly end up here. On 8 minutes, it's at 100 degrees C. And the examiners will always accept a little range of answers. Part C. Another student decides to melt some ice. The student melts 380 grams of ice at 0 degrees C. So let's convert that mass into kilograms. The specific latent heat of fusion of ice is 3.34 times 10 to the 5 joules per kilogram. So that's why we had to convert grams into kilograms to make sure they're all in similar units. Calculate the thermal energy needed to melt the ice. Select an equation from the list of equations at the end of this paper. So if you go to the end of the paper, we can see that this is the equation we want. Thermal energy for a change of state is the mass times by the specific latent heat. So Q equals mL. So specific latent heat. So that's why we need L. So Q equals mL. That's our mass in kilograms, and that's our specific latent heat. And the answer comes out as 126,920 joules. Question 2. The cyclist is riding a bicycle at a steady velocity of 12 metres per second. The cyclist and the bicycle have a total mass of 68 kilograms. Calculate the kinetic energy of the cyclist and bicycle. Use the equation. So kinetic energy is a half mv squared. So that's a half. Our mass is 68 kilograms and our velocity is 12. So square that. Make sure you square the 12 first and then multiply it by that and that. And the answer comes out as 4,896 joules. Part B. Describe the energy transfers that happen when the cyclist uses the brakes to stop. Kinetic energy is transferred into thermal energy. So it's obviously travelling at first, so that's what the kinetic energy is, and the brakes will get hot, so that's thermal energy. Part C. The cyclist starts to cycle again. The cyclist does 1,600 joules of useful work to travel 28 metres. Calculate the average force the cyclist exerts. So we're looking for a force. It's gave us energy and it's gave us a distance. So the energy is the same as the work done. So the equation we can use is work done equals force times by distance. Rearrange that so that force is the work done or the energy divided by the distance. So put the values in. Answer comes out as 57.1. I've just rounded it up to 57 because there was no decimal places for either of the answers that they gave us. Part D. An athlete uses a training machine in a gym. The display on the machine shows the time spent on the machine and the amount of energy transferred during a training session. Figure 1 shows the displays for two different sessions by the same athlete. Explain what the display shows about the average power of an athlete in each of the two sessions. Well, they've gave us the energy and they've gave us the time. So the equation that relates energy, time and power is power equals energy transferred divided by time taken. Now for 2 marks, we can say the athlete was more powerful in session 1, and that's because they transferred more energy. So in this session they transferred 45.2 kilojoules of energy, whereas in session 2 they only transferred 37.9 kilojoules, and you'll notice it was in the same amount of time. So they transferred more energy in the same amount of time. That's why they were more powerful in session 1. Now, if it was worth more than 2 marks, you could actually then go on to work out what the power was by doing the energy for the session divided by the time of the session. And session 1 comes out as 0.15 kilowatts, which is 150 watts, and session 2 comes out as 126 watts. And remember, 1 joule per second, so joules per second, is 1 watt. So power is always measured in watts. Question 3. A student has a bar magnet, a piece of iron the same size as the magnet, and some paper clips. Describe how the student could use these items to demonstrate temporary induced magnetism. So, if you touch the magnet with the piece of iron, as shown in this picture, so there's the magnet, north and south, and there's the iron. If you then touch paper clips with the piece of iron, with the magnet still touching the iron, the paper clips will be attracted to the iron. And that's because when the iron's touching the magnet, the iron becomes magnetic, or a temporary magnet anyway. And we can see that it's just temporary, because if we remove the magnet away from the iron, the paper clips will fall off the iron because the iron is no longer magnetic. So you can see, when I've pulled the magnet away from the iron's not a magnet anymore, and the paper clips have dropped off it. Part B. The student sets up the apparatus shown in figure 4. When the current in the solenoid is switched on, The solenoid attracts the iron nail. Describe how the student could use this apparatus to investigate how the size of the current in the solenoid affects the force of attraction between the solenoid and the iron nail. Okay, so if we note the position of the pointer before turning the current on, so here's the pointer here, which is attached to the spring. So as you turn the solenoid on, the iron nail is going to be attracted down, which is going to stretch the spring, and it's going to pull the pointer down on the ruler. So if we then note the position of the pointer after we've turned on the current, and then if we measure the size of the current with an ammeter, and then we repeat the above steps using larger currents, we will determine that the further the pointer moves, the greater the force of attraction between the solenoid and the iron nail. And that's what they were asking for us to find out. How the size of the current of the solenoid affects the force of attraction between the solenoid and the iron nail. Part 2. The spring constant of a different spring is 24 newtons per metre. That means you need to put 24 newtons on to make it stretch a metre. So that's our spring constant K. The spring is extended from its unstretched length of 12 centimetres. Now if that's in metres, we need to convert this into metres as well. So 12 centimetres is 0.12 metres, and that'll be our extension X. Calculate the energy transferred in extending the spring by 12 centimetres. Use an equation selected from the list of equations at the end of this paper. So the equation that's got the spring constant in is this equation here, and you'll notice it's also got the extension, and we're trying to work out the energy. So we've got everything we need. Energy is a half kx squared. So E equals a half kx squared, so that's a half times by the 24 newtons per metre times by 0.12 squared. Make sure you square the 0.12 first, then multiply it by that and then that, and the answer should come out as 0.1728. So I've just popped it down at 2 decimal places. Question 4a part 1. Figure 5 shows the vertical forces on an aeroplane. So you've got 8.4 kilonewtons going up and 7.5 kilonewtons going down. Use the information from the table to determine the size and direction of the resultant vertical force on the aeroplane. So what you do, always just take the smallest number away from the biggest number. You know that the overall direction is going to be upward because the upward force is bigger than the downward force. So 8.4 kilonewtons take away 7.5 kilonewtons comes out as 0.9 kilonewtons, and the direction will be up because up was the largest force. Part 2. The aeroplane is descending, which means it's going down. Figure 6 shows a diagram of the resultant vertical and horizontal forces on the aeroplane as it's descending. So vertically we've got 300 newtons going down, and horizontally we've got 400 newtons going backwards. Complete the diagram to show the resultant of these two forces. So if we were to add this force to this force, you'd end up with this force here. Now it's what we call tip to tail addition of vectors. So just take any one vector and then add the other one to it. So first let's follow this vector here, and then if we were to go 300 newtons downwards from that point, we'll end up here. Part 3. The mass of the aeroplane is 750 kilograms. So write down what you know when you know it. So there's the mass. Calculate the change in gravitational potential energy of the aeroplane as it descends from 1,300 meters to the ground. So that's our change in height, and we're trying to work out the gravitational potential energy. So that's our target. Gravitational field strength is 10 newtons per kilogram. The equation that we need is the change in gravitational potential energy equals mass times by gravity times by the change in the height. So we'll just pop the numbers in and the answer comes out as 9,750,000 joules. Part B. The aeroplane is powered by an engine that burns fuel. The fuel supplies a total of 6,500 kilojoules of energy every minute. The efficiency of the engine is 0.7 or 70%. Calculate the power output of the engine. So power is the energy per second. Now they've gave us the energy per minute. So we'll deal with that at the end. First of all, the equation for efficiency that will allow us to work out the power that comes out is the useful energy out divided by the total energy in. So we rearrange that. We get the useful energy out equals the efficiency times by the total energy in. So there's the efficiency. That was the total energy in. So it comes out as 4,550 joules every minute. Because remember, that's the amount of joules per minute. So by the time you've only got 70% of that left, that's how much you've got left. If you took that number and divided it by 100, that would be 1%. And then multiply it by 70, and that would be 70%. And that would give you the same value here. So I'll write that down just in case. So you may prefer to do it that way. Now, once we know how many joules we've got every minute, if we divide that by the amount of time in a minute, then that'll give us the amount of energy in a second, which is the power. So there's 60 seconds in a minute, so if we take that value and divide it by 60, that'll tell us how many kilowatts there are, which is the power. Part 2. Explain why the efficiency of the engine is less than 1, which would be 100%. Well, a lot of students get confused with this kind of question, and what I say is start with the equation for efficiency. So efficiency is useful energy out over total energy in. So why would the efficiency always be less than 100, or why would it always be less than 1? Efficiency is always less than 1 because useful energy out is always less than total energy in, because energy is always lost as heat to the surroundings because of friction. So it's only worth 2 marks, but if it was worth more than 2, you would expect a mark for each one of these things that I've underlined. Question 5. A resistor is connected to a power supply. The potential difference across the resistor is 6 volts. Which of these corresponds to a potential difference of 6 volts? So they're giving you alternative units for volts. So if we think of an equation for volts, well, voltage is current times by resistance. So current is in amps and resistance is in ohms. So 1 volt is equivalent to 1 amp ohms. Not amp per ohms, but amp ohms. Is amp ohms here? No, they've got amps per ohm, and we just had amps ohms. So let's think of another equation for voltage. Well, we've got EastEnders is the Queen Vic. Energy is charge times by voltage. So therefore, if we rearrange it, we can get voltage is energy over charge. Energy is measured in joules, charge is measured in coulombs, so 1 volt is equivalent to 1 joule per coulomb. And have we got joules per coulomb available to choose? Yes, we have. So 6 joules per coulomb. Answer C is correct. Part 2. The resistor remains connected for a period of time. The current in the resistor is 200 milliamps. So write down what you know when you know it. 200 milliamps, we'll divide that by 1000 and that'll turn it into amps. So that's 0.2 amps. A total charge of 42 coulombs flows through the resistor. So that's Q. Calculate in minutes the time taken for this amount of charge to flow through the resistor. So time is our target. So what equation do we know that relates time, charge and current? It's this one. Q equals I times by T. Let's rearrange that. So time is the charge divided by the current. So that's 42 coulombs divided by 0.2 amps, which is 210 seconds. But they wanted it in minutes. So 210 seconds divided by 60 seconds in a minute, that'll tell us it's 3.5 minutes. Part 3. Calculate the total energy transferred by the 6-volt power supply when a charge of 42 coulombs flows through the resistor. So we're looking for energy, that's our target. It gives us the charge and it gives us the voltage. So what equation do we know that connects energy, charge and voltage? It's our EastEnders, it's the Queen Vic. Energy is charge times by voltage. So put the numbers in and the answer comes out as 252 joules. Part B. The resistor becomes warm while there is a current in it. Explain why the resistor becomes warm. Okay, so collisions between electrons, which is the current flowing, and the lattice, which is the metal ions making up the wire, make the lattice vibrate more. So what I mean is that the kinetic energy of the electrons starts to decrease as the electrons collide into the lattice, and its energy from the electrons get passed on to the lattice. The more that the lattice vibrates, the hotter it is. Figure 7 shows a cardboard tube with a wire coming out from one end. There are two 10 ohm resistors inside the cardboard tube. A potential difference of 6 volts is connected between P and Q. There is a current of 1.2 amps in the wires. Deduce how the resistors have been arranged inside the cardboard tube. Okay, the first thing we need to do is take our Ohm's law, V equals IR, and rearrange that so we can find out what the resistance is. Now if we've got a voltage of 6 volts and a current of 1.2 amps, that means that the resistors in here have got a resistance of 5 ohms. Now, if we've got two 10 ohm resistors, if we were to add them one in front of the other in series, then their combined resistance would be 20 ohms. 10 plus 10 is 20 ohms. And we've got 5 ohms. So the resistors cannot be in series, so they must be in parallel. Since the total resistance is only 5 ohms, the resistors must be connected in parallel. The resistance would be 20 ohms if connected in series, so they're not connected in series. So they're connected in parallel like this, and that would give the equivalent of this. Now at GCSE, you no longer need to calculate resistance in parallel. It's in A-level physics now, but you still do need to have a basic awareness of it. Question 6. Figure 8 shows identical filament lamps connected together in a 12-volt power supply. Calculate the potential difference across each lamp. Okay, well, when components are in series, they share the voltage, and they're identical bulbs. That's why I've underlined identical here. So they'll have identical voltages on each bulb because they've got identical resistances. So if we take the 12 volts and just divide it equally between the 8 bulbs, each bulb will get 1.5 volts. Part 2. The power output of each lamp is 0.75 watts. Calculate the resistance of each lamp. Okay, so we're looking for the resistance, we've got the power, and we've just worked out the voltage. So what equation do we know? Well, we could just use power equals V squared over R, rearrange that to get R, so take our voltage and square it and divide it by our power. 3 ohms. That's the easiest way of doing it. I've showed you here an alternative method just in case they wanted to know what the current was as well. Explain with the aid of a circuit diagram the method a student could use to investigate how the resistance of a single lamp changes with the potential difference across the lamp. Okay, so the circuit that you need to set up, there's our lamp. In order to get the resistance, we need to use resistance equals voltage over current. So we need a way of measuring the voltage of the bulb. So we use a voltmeter in parallel. And we need a way of measuring the current going through the bulb. So we'll use an ammeter in series. And we'll also need some way of changing the voltage and seeing what the effect is on the bulb. So we'll use a variable resistor to allow us to do that. So measure the voltage on the bulb with a voltmeter, measure the current through the bulb with an ammeter, use the variable resistor to change the voltage on the bulb, get at least 6 different values of the voltage and the corresponding current value to calculate 6 different R values of the bulb. And then we'll be able to spot how the resistance of the lamp changes when we change the potential difference or the voltage across the lamp, which is what they were wanting to know. And that's the last question, is our 6 marker. So I hope that's been useful for you. There'll be more videos like that to come. Subscribe to the channel so you can receive notifications. Good luck with your mocks and any exams that you sit. Work hard, be nice, and bye for now.